Can everybody hear me up there? We're good? All right. So, as you saw in the email last night, we're giving people the opportunity to make up for a low midterm score by potentially substituting the final exam score for the midterm score. So, my gift to you. Also, some people ask for an opportunity to have a proctored exam, like in a room, so you have that option too. Of course, you can still do a take-home exam as you did the midterm. Any questions about any of that? The TAs will give you more details on all this. Yeah.
So are you only replacing the midterm scores with the final exam scores under a certain condition? Or
for most people, it'll be automatic if the final exam score will be higher than the midterm. Obviously, if it's not higher, we're not going to give you a lower score on the midterm or anything like that. So it's only going to help you, not penalize you. So we're trying to get people to do better and get a higher score if possible, study more, take the final seriously, because that can really help you retroactively, not just for the final exam. So that's the idea. Let's try to help you and motivate you and be generous. All right, so last time we talked about approximation algorithms for various NP-complete problems, including traveling salesmen and vertex covers and other NP-complete problems. Now we're going to do another approximation, an even more interesting kind. We're going to approximate proofs. We used to think that in order to prove something mathematically, you have to disclose the entire proof, and then of course the person who gets the proof can check to see if the proof is correct or not, if it's proving what it's intended to prove. But it turns out you don't have to disclose a proof and still convince somebody that you have a proof and that the proof is valid. It sounds, on the face of it, almost impossible, right? An impossible task. How can you prove something to somebody without telling them the proof itself? So it's kind of a meta-proof. And in some sense, it's an approximation of proving, because the proof is not completely 100% beyond doubt foolproof, but it's arbitrarily close to 100%. To 1.0 probability. And you'll see in a minute what we mean. It's called zero-knowledge proofs. But before we attack that, we need to talk about the problem of graph isomorphism. One can't simply walk into Mordor. So we're going to do a gentle introduction to graph isomorphism. So basically, it's the problem of giving two graphs, whether they're isomorphic. Whether a renaming of the vertices of one graph will still give you the same graph if you're presenting with both versions, the graph and its scrambling up of the vertices names. So it's an edge-preserving permutation of the vertices, basically. So for example, here's a graph, and here's another graph, and they look different, but they're not, right? How many can see that these graphs are identical? If you relabel if you take this node here, put it in the middle, and shift this node over, you'll get this graph, which means topologically they're identical graphs. So they're called isomorphic. And here's a more interesting example, less trivial example involving 8 nodes. This graph is isomorphic to that graph, even though they don't look like it when you draw them in a plane like this. But graphs are not about drawing things in the plane. Graphs are about topological connectivity among a set of finite nodes. So if you look at this graph here and this graph here, this purple node is isomorphic to that purple node, and this green node is isomorphic to this green node. So 5 is the same as G, 2 is the same as H, 8 is the same as C. And if you just relabel these nodes here with these numbers to these nodes here with these letters, you'll see that whenever a pair is connected here, a pair is connected there. The equivalent analogous pair is connected on the other graph, and it's an if and only if. If two things are not connected here, they won't be connected there. So topologically, they're equivalent. Any questions about what graph isomorphism means? Pretty straightforward, right? Now, it's known to be an NP, right? You can guess an isomorphism between two given graphs and then check to see if the isomorphism works by checking all the edges and all the non-edges to make sure all the edges are there, all the non-edges are not there on the other side, and then you'll know. So definitely it's an NP. Amazingly, it's not known to be either in P or NP-complete either. It's in this sort of nether region between these two classes, P and NP. Maybe one day we'll show it's polynomially time solvable. Right now, we're not sure. So we think it's a very difficult problem. We just can't prove one way or the other. But still, we're going to use this in another context. So why is graph isomorphism hard, like intuitively? If I give you two graphs that look kind of different, it's hard to tell if they're the same. How many say these two graphs are isomorphic? How many say they're not isomorphic? It's not easy. Nobody's voting, right? It's hard to tell. How many say any two of these graphs on this slide are isomorphic to one another? Any two of the five? Can you pick an isomorphism between any two of the five and say two of them are the same as each other, at least two? Maybe more, but at least two. How many say yeah? Again, you see it's hard to tell. But let me show you an animation. So this is an animation of morphing between this graph here and that graph there, right there. How many say these two graphs are isomorphic now? Good. Now you can see it clearly because I showed you a proof why it's isomorphic. But if I didn't, before I show you the picture, you see nobody voted, and nobody could tell for sure unless you take a long time to figure this out and look at all possibilities, and eventually maybe you'll stumble onto an isomorphism, but maybe not. It turns out not only these two are isomorphic, because there's the proof, all five are isomorphic to each other. So all five graphs that you're looking on this slide are all isomorphic to one another. Again, that's not obvious. So now you see why graph isomorphism is not easy, even for small graphs. Now imagine if all these five graphs had 10,000 nodes in them, not just a few. That'll be horrendous to try to figure that out, whether any two are isomorphic. So now we can talk about zero-knowledge proofs. So zero-knowledge proofs is proving that a graph is isomorphic to another graph without showing you the isomorphism. Because I could have told you earlier that these two graphs are isomorphic. I'd say, yeah, take my word for it, they're isomorphic, don't worry about it. You still won't be convinced because you don't know what the isomorphism is, and you may take my word for it, but you wouldn't bet your life on it. But once you see the proof, you could bet your life on it or $1 million on it because they are the same. The proof establishes the isomorphism. So in the context of proving isomorphism without disclosing it, there's many applications, like friend or foe systems. The military plane comes in, and there's a ground station that's protecting a base. This plane is not known to be a friend or an enemy, a friend or foe. This ground station here has a binary decision to make, very dramatic decision. Either if it's a foe, this is wartime, so it needs to shoot this plane out of the sky before it can come in and bomb you or strafe you. If it's a friend, it should absolutely not do that and instead allow you to come in and land safely on the base. Now, the false positive and false negative errors in this scenario are very severe. Either you're destroying a friend, which at least will court-martial you or worse, or you're letting an enemy come in and do what they want, which means you could be destroyed instead. And either way, you'll have a very bad day. Not to mention the people on the plane potentially. So how does a plane identify itself? And by the way, this is a general scenario. It doesn't have to be a plane. It could be a person walking in or a ship or some other scenario, right? Two groups meeting up towards each other. And the situation doesn't even have to be hostile. It could be a business situation. We have a cash register and a credit card. Credit card is trying to make a transaction, convincing the register of something, but without disclosing too much information. So the plane doesn't want to send over the air some password, right? If the password, say, was blue sky, the plane could come in, transmit blue sky, let me in, I'm a friend. But then the enemy can hear that, and next time the enemy can send in drones or planes and say blue sky, and spoof your password from before, and then it'll come in and you'll be in trouble. So you don't want to transmit the password over the air, not even in an encrypted format, because encryption could be broken, or the enemy can take the encrypted format and send the encrypted format over, just record it and send that over the air, and same problem happens. So you want to keep the password from ever going over the air. But yet you need to convince the ground station that you know the password. And the password is the isomorphism between two large graphs. These two graphs, G1 and G2, are large and they're complex and they're web publishable. They're on the web. Everybody can see them, including your friends, including your adversaries as well. So they're literally posted on the web for everybody to see. Those are not secret. In fact, they're highly visible to everybody. What is secret is the isomorphism in red, how this one isomorphs and transforms to that one. The isomorphism, the permutation that proves the isomorphism. That's the red isomorphism in this squiggly line. And the plane knows that isomorphism. When I said the plane, I mean the plane's computer The pilot doesn't have to memorize anything. It's computer. It's doing the job, right? The isomorphism is stored aboard the plane and nowhere else in the universe. So when you produce the plane, you hardwire into the EEPROM, say, of the motherboard of the circuit of the computer of the plane, the isomorphism, which is just a permutation, right? It doesn't take very much space to store a 10,000 node graph permutation. It's just 10,000 integers, basically. It's just a few K of storage. So it's stored aboard the plane and nowhere else. This isomorphism is not stored on the web. It's not stored on secure servers on the base or in the Pentagon or anywhere else. Literally, it's only on the plane, and that's it. You can easily do that when you manufacture a plane. Create an isomorphism with random numbers, burn it onto the chip, then destroy that knowledge and don't store it anywhere. And now the chip is the only thing on Earth that has that isomorphism stored in it. So this plane needs to convince its ground station that it has the isomorphism, that it knows the isomorphism, but not disclose what it is, not even in encrypted form. So how do you do that? The isomorphism must remain secret. So what you do is this. The plane creates a random isomorph of one of the graphs, right? To call it G. G is not secret either. The plane transmits G over the air in the clear, not encrypted, to the ground station. So now we have three graphs, G1, G2, and G is an isomorph of G1. It's easy to create an isomorphism, right? Just randomly scramble all the nodes, and you got an isomorph, right? So that's easy to do. So it transmits the isomorph here. Now the ground station comes back, and but before you even say that, let's just say the two graphs, G1 and G2, are isomorphic. The plane knows the isomorphism. The plane generated an isomorph of G1 that we call G, so the plane knows the green isomorphism because it generated it randomly. Now, if it knows the red isomorphism and the green isomorphism, the plane also knows the blue isomorphism between G and G2 because the blue one is just a composition of the red and the green. How many can see that? Just the two composed. A permutation of a permutation is a permutation. Right? Permutation is composed to give you more permutations. Permutation is just a shuffling. Right? So the plane now knows all three isomorphisms, but the ground station doesn't know any of them. But the ground station can now, after it gets G broadcast to it, it can ask to see either the blue isomorphism or the green isomorphism, one of the two. We don't know which it will prefer to see, so it can ask to see the green or the blue. Once it does that, we give him the green or the blue isomorphism between G1 or G if it asks for the green, or we give him the blue isomorphism between G2 and G if it asks for the blue one. And then the ground station can verify that the isomorphism you just gave it, whichever one it asked for, is correct isomorphism. That it actually maps the nodes of this graph to this other graph in a correct way that preserves edges and non-edges. So it checks to see if you were right. Now, if the plane didn't know the isomorphism in red, all it can do is scramble either G1 or G2, and if the ground station asks to see the correct one from which it got scrambled, you will be lucky and be able to give it to him. But if it asks for the other one, you won't be able to do it if you don't know the red one. How many can see that? Because if you knew the green one and the blue one both, so that you'll be able to give it to the ground station whichever one it asks, if you knew both of the green and the blue, you'd know the red by composing them trivially. So if you don't know the red, you can't know both the green and the blue. If you know the red, you know all three. But the ground station can ask to see the green or the red, but not both, and then you give it to it. So if you're lying, if you're spoofing, if you don't know the isomorphism in red, which is a secret, what are the odds that you'll be able to pass one round of this with the ground station that then checks your answer? Yeah, so 50-50, right? How many can see 50-50 odds of not being caught on a lie? Okay, well 50-50 odds is not great odds for either being court-martialed or dying that day on the false positive or false negative outcomes of this thing. So how would you increase the odds in your favor? Because the odds right now, the odds are not in your favor. That's a line from some movie, isn't it? The odds are, may the odds be ever in your favor. How do you increase the odds? Yeah. Do it a bunch of times. How many times do you need to do this? If you do this 2 times, what are the odds now of getting caught on a lie if you're a liar? if you do it twice. 50-50 chance you'll be caught the first time. 50-50 chance you'll be caught the second time. 25% chance you won't be caught, right? And if you do it k times, the odds decrease exponentially with k, right? So you repeat this k times, and we'll see how k has to be in a minute, how high it has to be to get reasonable behaviors here. But the probability of cheating is 2 to the minus k if you repeat this k times. How many see that? Because it's half and a 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 half. Those are the odds of not getting caught if you're trying to pull something fast, if you're trying to cheat through this process. So if you do this k times, and k is, say, 10. If you do this 10 times, what are the odds of a cheater actually getting away with cheating? If you do it 10 times. 2 to the 10, or 2 to the minus 10, which is 1 in roughly 1,000, 1,024. If you do it 30 times, what are the odds of getting away with something fishy if you don't know the red isomorphism? If you do it 30 times, roughly. I'll throw some numbers around. 1 in a billion, roughly, right? Remember powers of 2? We had long chats about that. So, 2 to the 10 is 1,000, 2 to the 20 is a million, 2 to the 30 is a billion, roughly, plus change. So 1 in a billion is good. It's good odds. There's a bigger chance you'll win the lottery than get away with 30 rounds of this if you're lying, right? How many can see that? Yeah, because odds on lottery is only 1 in 100 million or something. If you don't like a billion, make it 40 rounds, then it'd be 1 in a trillion, right? 1 in a trillion is probably, bigger chance you'll be hit by lightning, sometime next year than get away with this. And certainly if you do it 50 rounds, you'll be. So you don't need 1,000 times or 100 times. 30, 40 times is more than enough. And that can happen very quickly because there's nothing here that's computationally intensive. It's all pretty straightforward computations, checking isomorphisms. I guess another isomorphism is linear time, right? So, yeah.
I'm a little confused on this broadcast step. So basically, someone broadcasts like the blue or the green congruency, correct?
Well, so first we broadcast the graph G, and then the verifier asks to see one of these two things, the green or the blue. And so then you comply. If it wants to see the green one, you send over the green one over the air, clean, unencrypted, clear text. If it wants to see the blue one, you send the blue one. If you want to see the green one, you send the green one. And then it checks to see if you were right, if that was an isomorphism. It's not going to ask for both, and you're certainly not going to give it both.
Okay. It's just the verifier text. It says like G is congruent to G1 on the last.
Yes. In other words, G is an isomorph of G1.
But then it shows a blue congruency symbol when that one's green.
Yeah, but if G is isomorphic to G1 and G1 is isomorphic to G2, G1 is isomorphic to both, right? Because G1 and G are the same, and if both of these are the same and one of them is isomorphic to the third, then both are isomorphic for the third. Composite to isomorphism. So if you have an isomorphism between two things, and one of them is isomorphic to a third thing, both are isomorphic to the third thing, not just that one, by composition, right? A permutation of a permutation is another permutation. Yeah?
What is the strategy not suffer from the same issues of encryption? Because if the plane is shot down, someone can salvage the chip, or potentially encrypt it.
Good question. Why doesn't it suffer from encryption issues like, the plane is shot down is saying now, the enemy gets a hold of the plane, dissects the chip, sees the isomorphism. What do you say to that?
There's really to be some log of that plane was shot down, and now you can't use its tag anymore because we know that plane doesn't exist.
Every plane has a different pair of graphs. So if one of your planes goes missing, if one of your F-22 Raptors goes missing, you notice, right? The pilot didn't check in for a few hours, whatever. You don't just let it go. And so you basically know that that plane is missing, and nobody can spoof that plane anymore because every plane uses a different isomorphism. Every plane uses a different pair of G1 and G2. They're etched into the computer's memory on production, and they're different pair for every plane. So every plane needs to identify itself as that plane. So if you're saying, I'm plane so-and-so, and, they can see your plane, but, so you're proving you're that particular plane. So when your planes get shut down, nobody cares to see the isomorphism of that plane anymore because they know it's gone. So if you try to be that plane again, they'll know that you've been shut down and you're an imposter. If you're trying to mimic the plane that is already out of the loop and decommissioned or shut down or not in action or whatever, or out for repairs or whatever. So even if they see even if they can detect the isomorphism when a plane is shut down, it doesn't hurt any of the other planes that are in play. And again, this scenario doesn't have to do with planes necessarily. It could be with ships or cars or vehicles or even in transactions in the business world. Credit cards can play this game with cash registers. So you don't want to necessarily, credit card, most credit cards now have smart chips in them, and you don't want to disclose the account number to the merchant because the merchant may be nefarious and may use it for bogus purchases, or somebody may eavesdrop onto their network. That, the vendor may be honest, but somebody can hack into their system and get your credit card number off of their computer, and then same thing will happen to you again, some identity theft or credit card fraud. So you want to convince your credit card needs to convince the cash register or the vendor that it's a valid credit card with a valid account number, with a valid balance, and so on. They can play this game back and forth and not disclose the actual account number. Just convince the cash register that the account number is valid and you're in possession of it. And you can use the same technique here. How many can see that? This is the same scenario, right? So it doesn't have to be some warlike scenario. It could be just a mundane, everyday business transaction kind of scenario. And it's called zero knowledge because nothing is leaked about this isomorphism through this interaction. Because you can generate an isomorph, but you can say, well, doesn't this ground station or eavesdropper, if you're an enemy, the eavesdropper, don't they possibly gain some information by hearing the isomorph that you're transmitting in the clear over the air? Well, no, because they can generate as many isomorphs as they want. If you're an adversary and you see an isomorph, well, everybody knows what G1 and G2 are, including the adversary, and if they want isomorphs, they can generate them linear time each, so their heart's contained by the trillions. They don't need you for that. So they're not getting any information or any computational advantage over you by seeing the isomorphs going back and forth. Okay. So, in some sense, this is kind of an approximation of a proof, of a mathematical proof. You're proving to somebody you know the isomorphism, but without disclosing the isomorphism. And by the way, the isomorphism, when I say isomorphism, don't take it too literally. I mean, yes, it's an isomorphism between two graphs in this example, but an isomorphism can encode an arbitrary secret or message or piece of text. How many can see that? Because all it is a permutation. And you could, by having a large enough permutation, think about a permutation as just the permutation of the integers from 1 to n. And by putting certain integers before other integers and so on, and looking at them in pairs or triplets, you can encode arbitrary messages, arbitrary characters from a large alphabet. Okay, so it's not just a permutation, it's arbitrary knowledge that you're encoding, whether it's account numbers, secrets, some secret email or hidden message, or whatever people want to encrypt, or convince somebody that they're in possession of without actually disclosing that thing. So this is a beautiful protocol. Any other questions about this? A protocol is just an algorithm, by the way. Everything in life is an algorithm of one kind or another, usually heuristics, not exact algorithms. But there's a few things you need to be careful here. One of them, you don't want to generate the same isomorph 2 times in a row through different phases of this iteration. How many can see why? Why is that? What if you generate the same isomorph twice by accident, not even meaning to do that?
If he asks for the other one too, then the eavesdropper will get it.
Yeah, if you generated the same one twice, first time, he'll ask to see the green, and second time, he may ask to see the blue, and if somebody hears the green and the blue for the same isomorph G, they can compose it very quickly in linear time, and then they'll know the red one, so you just leaked it inadvertently. So you have to be careful. Now, if you generate a random graph with 10,000 nodes, what are the odds that you'll be able to generate the same random graph twice in a row? even after a million trials. Very, very little chance of that. So you don't usually have to worry about it. But if you are worried about it, just keep track of all the isomorphs you ever generated and just don't generate the same one twice. You can easily check. You only need 20 or 30 isomorphs each round, and you can store them all or whatever, and just be careful not to generate the same one twice. But you don't even have to do that. The chances of generating the same 10,000 node graph twice in a row, even a million trials apart, are so small that they're even smaller than you'll be able to cheat in 130 rounds of that, right? So you don't even have to worry about it. Another thing you have to be careful of is that make sure that these two graphs are not easily detectable for isomorphisms. So if these two graphs are both cycles, and that's it, very simple graph, just one long cycle, how hard it is to determine whether two cycles are isomorphic? Doesn't take much. They are isomorphic as long as they have the same number of nodes in them. Right? Or if the two are trees, it turns out that tree isomorphism is easier than general graph isomorphism. There's a straightforward polynomial time algorithm to determine whether two trees are isomorphic. In fact, you can do it in linear time if you try hard enough. Also, if these two graphs are isomorphic, and in this graph there's only one node of degree 127, 10,000 node graphs, there's only one node of degree 127 here, and only one node of degree 127 there, what do you know about these two nodes via the red isomorphism? These two nodes are isomorphic. They're the same node in both graphs. How many get that? So equal degree nodes get mapped to equal degree nodes if the two graphs are isomorphic. You can have a graph with degree 7 on a node, have that node of degree 7 mapped to a degree 3 node over there. That ain't going to be an isomorphism. So make sure that the degrees are not all different than each other, otherwise you can easily determine the isomorphisms for graphs like that. So it's easy, again, it's easy to do. Make sure that in a 10,000 node graph, all the degrees are say 50,000, no more, no less. And then you can't use the degrees to help nail down the isomorphism unless you know the isomorphism. And so, again, you're okay. So for example, here's what I'm talking about. In this graph here, no matter which isomorphism you have between these two graphs, this node here will map to this node here because the degree here is 2 and the degree here is 2. That must happen in any valid isomorphism. How many can see that? Because edges must map to edges and non-edges must map to non-edges. Okay, any other questions so far? So it's just a beautiful trick, right? It's a very nice algorithm. How many have participated in this kind of algorithm in your daily lives before? How many have had this experience in your daily life? Or an experience isomorphic to this, I should say. No pun intended. Not exactly this, but something very similar. Like how, what, when? RSA encryption, okay. All right. How about something even more obvious that you did personally many times in your life? Any thoughts? So it's not wrong, but let's find an even more mundane example. Because a lot of people may not know what RSA encryption is or whether it relies on isomorphism or something else. Okay. So let's say I want to test your knowledge. Let's say you're trying to convince me that you know a lot of stuff, right? We've just been through this course. It's almost over, 3 months long, right? I taught you a lot of stuff, hopefully a lot of stuff. There's literally hundreds of things that we went over this in class, right? Hundreds of concepts, proof techniques, problems, solutions, ideas, definitions, transformations, all sorts of interesting things, heuristics. And I want to make sure you know all 500 things. And there are about hundreds and hundreds of things. I actually made a list. I'll show it to you next time. It's a long list of all the stuff we went over in this course. Dovetailing is one of them. Diagonalization is another. Pigeonhole principle, that's a third thing. Triangle inequality, that's a fourth thing. Literally, there's 500 things. I'm not kidding. I just named 4. And you want to convince me you know all these 500 things. We don't have time to test you on each and every one of those 500 things. So what I do is I throw a random problem at you. And you solve it, give me back the solution. I check it to see if your solution is correct. But I don't know if that solution that you just happen to know represents your knowledge of 500 other things. So what we do? Iterate. I give you another question. You give me a solution. I check it. This is exactly what's happening here. We go through maybe 6, 7, 8 rounds of this. What is this process called I just described? It's called a final exam or a midterm. That's exactly what tests are. Now, maybe you'll get very, very lucky and you didn't study the 500 things that I hoped you would, and you only studied the 7 that I just happened to ask you on the exam. And you happen to get those right, and I believe you know all 500 things based on this 7 answers that you give me, and but that's not very likely to happen, right? Extremely unlikely, in fact. And you certainly don't want to bet, your performance on a course on just being so lucky, of just guessing what exactly will appear on an exam. So an exam, a test, is essentially one of these protocols. How many can see that? It's the same idea, and an exam works highly reliably for exactly the same reasons this works highly reliably. Because if you're trying to subvert this protocol, whether it's zero-knowledge proof or an exam, it's not easy to do with high probability. Okay, any questions about that? So yes, most of you have already done this all over the place in your own lives. In fact, you're about to do this one more time, or several more times next week when finals come around, right, in the various classes. Put another way, this is a sampling process. This samples your knowledge in a way, just like an exam does, in a way that statistically reflects everything you know without you having to transmit everything you know to me, and we'll both have a lot of work to do then if you're trying to do it 500 times for all 500 things that you ought to know by now. And luckily for the TAs, they won't have to grade 500 questions per person. You won't have to answer 500 questions. So it's very effective. It's a sampling process. Okay, any other thoughts or questions about this? So this is a codification and a mathematical proof that such a process actually works, and you can do it with graph isomorphism or other NP-complete problems. Here's a version of this with graph colorability. So the plane knows the coloring of a graph. Right? Call it psi or whatever. Knows the coloring of this graph, the 3 coloring of this graph. But everybody knows the graph, but nobody knows the coloring except the plane. Now we know coloring is difficult. We already proved it's NP-complete, even for planar graphs, even for max degree 4 graphs. So how does the plane convince the ground station that it knows the 3 coloring of this very large graph without actually disclosing the coloring? Well, very similar proof as before, very similar protocol or algorithm as before. Basically, create a random isomorph, G2, and because it's an isomorph, it has the same coloring as the other one via the isomorphism. Isomorphic nodes get assigned the same color on the other side, and that will be a coloring too, a valid 3 coloring. How many can see that? You can paint the isomorph the same way you painted the graph. Just respect the isomorphism correspondence, and then you'll be good on the other side. So the ground station asks to see either the isomorphism between the two or the coloring of the isomorph, not both. And if you can successfully either report the isomorphism or separately correctly give it the coloring of the isomorph, it is with higher and higher probability convinced that you know the coloring of the original graph. How many get that scenario? That wasn't a lot of people, so let's go over it again. So everybody in the world knows the graph, but only you know the coloring of the graph. So to convince somebody that you know the coloring of this graph, you generate an isomorph. Nobody knows how to compute isomorphisms from scratch unless you know them. We already talked about that, right? So you create an isomorph, and this ground station asks to see either the isomorphism in green or the coloring of the isomorph, this psi prime, but not both. And if you can successfully either show the ground station how these two are isomorphic, and separately on other occasions show them that this is 3 colorable and you know the coloring, but not both, because if you give it both, it can compose the two and get the coloring of the original graph, which is your secret. That's the one in red here. You don't want to give that away. That's the Xi here. So if you can convince the ground station that you know the isomorphism, or that you separately, many times over and over again, know the coloring, the sweet coloring of the isomorph, it's more and more convinced that you know both. Because if you didn't know the original coloring of the graph, you couldn't pass these tests over and over again, either or, disclosing the isomorphism correctly in a checkable way, or disclosing the sweet colorability correctly in a checkable way of the isomorph. How many get it now? Okay, that's not a lot of people. I'm surprised, because it's pretty much this similar situation to before, just with a different problem, with a coloring rather than with an isomorphism strictly. Because coloring is very hard to determine unless you're given it. We already know that. We proved that many times over. Isomorphism is very hard to determine unless you're given it. We already saw that at the beginning of class. I showed you graphs. You couldn't tell me which ones are isomorphic or not, even though all 5 were. So isomorphism is hard. Coloring is hard. So if I know the coloring of this graph, and I give you an isomorph of this graph, whoever sees the isomorph doesn't know the coloring and doesn't know the isomorphism. But if I know the coloring and I know the isomorphism, I know the coloring of the isomorph simply by pushing the colors through the isomorphism, and I know how to color the isomorph. But your adversary doesn't. So you need to check 2 things, that these 2 are isomorphic and you know how, and that you also know the colorability of both of them, the 3 coloring of both of them, and it doesn't know that either. So you can check to see one or the other. It forces you to give one or the other to him, and then they check. And if you can do that consistently, the 2 must be true at the same time. Otherwise, if they weren't, you wouldn't be able to fool the verifier so many times in succession, because if you didn't know the coloring of the original graph, you wouldn't know the coloring of the isomorph either. How many get that? Not really? Not just a few of you? Let's move on. I don't know. I don't want to spend the whole session on this, but you can do this with any NP-complete problem, is my next point. So if you didn't get that one, I'm not sure if you'll appreciate this point, that any problem in NP, like satisfiability, you can convert that to a graph colorability and then push the graph colorability through this protocol and thereby have a 0 knowledge proof for any problem in NP, not just isomorphism, not just graph colorability, but satisfiability, or any other problem in NP. How many get that part? Okay, well, wow, it's amazing. A lot more people got that part than the specific instance on the previous slide where I just used colorability. That's all right. I'll take it. You know, I won't ask why that is. Okay, so we already mentioned the caveats. The graphs must be large. You know, small graphs won't cut it because it's easy to permute small graphs in all possible ways and detect the isomorphism if there is one. And degrees, you know, better be repeated, and the graphs should be kind of complex enough. You shouldn't use the same graph twice. And there's lots and lots of applications of this all over the place. Any other questions about any of this? Yeah.
So is determining whether 2 graphs are isomorphic NP, or is finding the isomorphism NP?
So we don't know if graph isomorphism is NP-complete. We know it's an NP, but we don't know that it's in P. So it's almost as good as NP-complete as far as practical purposes go. Now, he's asking whether it's NP-complete to determine an isomorphism or just to determine whether an isomorphism exists. In other words, is it harder to determine what the isomorphism is or just whether it exists or not? What do you guys say to that, just as a kind of gestalt answer? What's harder, to compute a satisfying assignment or to tell whether a satisfying assignment exists? What do you say to that? What's harder, to optimize or decide? How many remember that slide where we talked about it? Good. Remember 21 questions or 20 questions? They're the same difficulty. Right? If you can do one, you can do the other. How? Play 20 questions with, if you can play 20 questions with a decider and thereby convert it to an optimizer that actually gives you the answer, 1 bit at a time. Modular polynomial time, you have to go through a bunch of rounds, but not too many. Right? So both are equally difficult with respect to polynomial time solvability. The polynomial time of the optimizer will be slightly larger than that of the decider, but they'll still both be polynomial or still be not polynomial. Together they stand, together they fall. That's the whole premise of NP-completeness. Yeah.
So far, for these examples you've given, they depend on a one-way function where it's easy to produce an isomorphism
Yeah.
from a graph, but it's not easy to verify that isomorphism unless it's given to you. Are there other things that could be substituted for this kind of isomorphism thing, or are you?
Yeah, there's other things. We'll talk about that in a minute, but he's saying it's not easy to compute an isomorphism, but it's easy to verify one if it's given to you that it is an isomorphism. Yeah, all of NP has that characterization. It's not easy to compute a satisfying assignment, but if I give you one, you can tell if it's satisfying or not simply by plugging it in and see what it boils down to. So all of NP has that characteristic. It's hard to come up with solutions, but easy to verify them. In fact, that's an alternate characterization of NP. But it gets more interesting than that here. It turns out that the set of problems or languages for which you can do this kind of zero-knowledge protocols is not just NP, it's all of P space, all of it. So it depends on the power, the computation power of the prover and the verifier. The prover is the plane, the verifier is the ground station, right? So the prover could have unbounded power, literally infinite computation power, could be omniscient and malicious on top of being omniscient. Right? The verifier has to be honest and can have limited power, and this still works. Right? It's complete if a statement is true, an honest verifier will be convinced, at least with very high probability, that the thing is true. Right? And it's sound if a statement is false, even an omnipotent, malicious prover cannot convince, a normal, limited verifier that that thing is true if it isn't, right? So the induced complexity class depends on the verifier's abilities. If the verifier is polynomial time and is deterministic, then the induced class is NP. You can do this for any problem in NP. If you allow probabilistic random bits to the verifier, the induced class is called interactive proof, IP, and in 1992, Adi Shamir proved that IP is equal to P space. They could do this for any problem in P space, not just problems in P or NP. P space is potentially considerably bigger than NP. P space contains NP, and they may be equal. That's another open problem, right? We talked about that a few weeks ago. Now, why is it that intuitively random bits help you to compute? I can give you a couple of different intuitive solutions. These are not mathematical proofs. These are intuitions. If you have a random number source, pseudo-random number, or better yet, true random number, it's very hard to come by true random bits. But Neumann already said that famously. He said that anybody who tries to come up with numerical means to produce random digits is, of course, in a state of sin. He meant that mathematically, but also figuratively. Why do random bits help?
First, are this examples we showed that were on the slides, are those probabilistic or deterministic verifiers?
For those, they were deterministic. So the induced class is NP, and we just chose problems in NP, satisfiability, colorability, and other problems in NP. But generally, you can do this for all of P space if you're allowed random bits. So the reason random bits are effective in computation, they give you a superpower, is, I give you two reasons. One is they help you to better sample a solution space. You can, using random bits, go all over the solution space, try different solutions using the randomness of the bits, construct sample solutions all over the place, and potentially find global minima better than if you couldn't produce random bits and you were doing more systematic, kind of locally expanding kind of search and that kind of thing. So that's one intuitive reason. The other intuitive reason is more subtle. How hard it is to determine whether a string is random or not. Not a trick question. You've seen this before several times. Determining whether a string is compressible or not, i.e. random, how hard is that? Let me ask you this. Is it decidable? How many say yes? How many say it's undecidable? Where have you seen this problem? On the last two homeworks, right? So it's very hard to determine if a string is compressible. Compressibility is equivalent to randomness, or lack thereof, right? If something is highly random, it's not compressible. If something is very ordered and structured, it's highly compressible. So if you have access to random bits, you essentially have access to strings that are very, very difficult to compute, and if you have access to those, you can usurp the difficulty of computing them because you already have them, you're giving them, you are being given them by virtue of having a random number generator on your hands, a true random number generator, and then you can exploit that to solve things more efficiently that you couldn't solve efficiently before. That's another intuitive reason why randomness helps in computation. These are not proofs, these are intuitions, which are probably more useful to you than proofs. Yeah?
Did the verifiers on the previous slides randomly ask for one answer or another? How is that deterministic and not probabilistic?
Because we don't care how it asks to see these two graphs. It's up to it. If it's probabilistic, you can flip a coin. If not, you can use a pseudo-random number generator, like a congruential multiplier, like the rand function does in C or C++ or Java. Every programming environment has some random number function that gives you random bits. How many have used random number functions? Of course, they're not true random. They're pseudo-random, or they're arithmetically designed to give you bits that are not that distinguishable from random bits. So it can do one of those, and it's perfectly deterministic. Your Java compiler is perfectly deterministic, yet it produces random bits for you when he asks for them. It's just not true randomness, it's pseudo-randomness, or arithmetically computable bits that are hard to distinguish from random ones. That's how it's deterministic. But how it does it, we don't care. It can flip a coin. It can literally flip a physical coin if it wants to. It can have a little servo motor that goes click and put a quarter on it, and you push a button and the quarter goes flying, and if it comes up heads, you ask to see the green one. If it comes out heads, you ask to see the blue one. You can do that if you want. Or whatever other means you care to. You can ask for the system time in nanoseconds, and then use the very last bit of that number. That will be pretty random for all intents and purposes. How many can see that? Yeah, because it's not truly random, but there's lots of ways to simulate randomness deterministically if you so choose. Now, if you want true randomness, you can have a whole course on that very concept of randomness and what it really means and how to produce it and how to test for randomness. And that's a very deep subject. Okay, let's talk about the Turing test. We're switching gears now. I want to present that before we finish the course. So the basic question is, can machines think? And the problem is, we don't know what think means. And we don't even know what intelligence really is. I don't mean smart intelligence like Einstein or Stephen Hawking, but I'm talking about just acting in a normal, intelligent way, being able to avoid obstacles and drive cars and hold a job and study stuff and invent things. It's things we humans do all the time. But we can't define what it is. We typically know it when we see it, but we don't know exactly how to define it, what characteristics to give it, or some mathematically define it, or anything like that. The Supreme Court famously, probably almost a century ago, had to grapple with the definition of pornography, because there's laws pertaining to pornography and so on, in indecency, and they tried very hard to define what it means for something to be pornographic, but they couldn't. Any definition that they tried to come up with, there were counter-examples and special cases, and famous Renaissance art shows a lot of nudity, but nobody calls that pornographic. But it depends on the context and on the time and on whoever's looking and the background and society and the culture and the norms at the time, and those change all the time. It's very hard to define. But finally, they just give up, and raised their hand and said, we can't define it, but we know it when we see it. That's sort of their working definition. And that's true to this day. In a court of law, they still use this functional definition. And so intelligence is the same category. We know intelligent behavior when we see it, although we can't define it. But it's a bit problematic. So if I ask you, which ones of these entities is intelligent, which ones of these can think, right? And there you have stones and rocks and paramecium and viruses, insects, mammals, and computers, and it keeps going to smarter and smarter entities. Now here we're going to science fiction entities because it's hard to come up with real-life examples of these yet. So we resort to, you know, Terminators and data from Star Trek and Star Wars robots and C-3PO and R2. This is HAL 9000 from 2001: Space Odyssey. How many have seen that movie? It's one of the best science fictions ever produced, even to this day. Agents from the Matrix, Cylons from Battlestar Galactica, and of course humans on the high end, because everything is measured in our image. We are kind of a self-centered, selfish kind of species. We haven't grown much yet. We're working on it. But so everything is comparing to us. It's hard to tell which ones of these can think, right? I mean, everybody can tell a stone can't think. You know, which stone is this, by the way? It's a particularly smart stone. It's a Rosetta Stone. So, but even so, that stone cannot think. Most people would agree that insects cannot, you know, think. They act in primitive ways. They can forage for food and stuff. Chimps, actually, some chimps were taught sign language. There are chimps that can sign several hundred words, vocabulary, and the chimp can say, "I would like a banana." And not an apple, not an orange, but a banana specifically. But of course, even chimps, even if you teach them to sign, they still can't do calculus or algebra or, you know, answer questions about automata theory and that kind of thing. They have trouble with abstraction. Of course, a lot of us have trouble with abstraction too, as we well know. So that can be the test for intelligence. But it's hard to answer these questions. Well, Alan Turing in 1950 wrote a single author paper called Computing Machinery and Intelligence. And this paper ushered in the entire field of AI. And in the very first paragraph, he says, "I propose to consider the question, can machines think?" And he says, "This should begin with the definitions of the meaning of the term machine and think," very incisively. And by the way, this first section of his paper is called The Imitation Game. And that's alluding to the Turing test. And now you know where the name of the movie came from, The Imitation Game. It was the name of the first section of his famous paper that essentially invented the field of AI in 1950. So on top of everything else that he did, we studied his work like for half this course, right? Decidability and undecidability, the Chomsky hierarchy and all that, and Turing degrees. And now, you know, we're talking about his other lesser-known contribution in the invention of artificial intelligence. So he proposed a functional test. He said, play Q&A with this thing that you're trying to determine whether it's intelligent or not. And after, say, 20, 30, 50 questions for half an hour, you tell us if you think it's intelligent. And that thing is sitting behind a curtain or behind a brick wall or whatever, so you can't be biased by the way it looks. So if it looks like R2-D2, or, you know, if it looks like, you know, something that you're not familiar with, you don't just write it off because it doesn't look and speak like you. So you just interact using texts. So it's very egalitarian test. It's just by the way it behaves, not the way it looks. Okay. So you don't want to bring in biases unnecessarily. So you can ask it to add things together. You can ask it, you know, to play chess with you for a couple of rounds. And notice that when you ask it to add things together, it deliberately pauses for 30 seconds and then gives you the correct answer here. So if you gave it the right answer in 1 millisecond, you can sort of tell it's superhuman, and it's therefore probably not human, because humans can't add up millions of numbers per second like computers can, or even billions per second like computers can. So you don't want to have the timing interfere with the analysis either. So you can have arbitrary pauses, and the timing is deliberately fuzzied up or potentially delayed just to prevent kind of timing type of attacks in trying to figure out what's going on behind the wall. And he called this imitation game. Now we call it the Turing test. Okay. Any questions so far? So he gave a very straightforward, practical test to determine or detect intelligence. He said, you have a brick wall, somebody behind the wall, you're trying to determine whether it's intelligent, you interact with it, a bunch of Q&A, say half an hour or an hour, and after that you tell us what you think. Right? So you're trying to distinguish the case where there's a human on the other side, or a computer, a machine, a brick, you know, a dolphin, a chimp, a robot, whatever it is, you're trying to distinguish these two cases. That's the purpose of the test. In particular, you're trying to determine whether it's intelligent, not whether it's human or not specifically, but whether it's intelligent like humans are intelligent. Why like humans? Because the person doing the testing is human, and it's trying to figure out if that thing is like it, basically. It's a comparative test. It's not an absolute test. It's a relative test, relative to whoever's doing the testing. So that thing is trying to convince the tester that it is intelligent, whether it's another person behind the wall or another computer or some other entity, you know, an alien from space or whatever. So it was the first deep investigation into whether machines can ever think or behave intelligently. It ushered all of AI, decoupled the notion of intelligence from the notion of human, because now it's not testing for a human behind the wall, it's testing for intelligence behind the wall. Before, we kind of confused the two things as the same, but they're not necessarily the same. Human and intelligence is not always the same thing. Right? Some people will swear their dogs and cats are intelligent. Right? And on the other hand, some humans are not necessarily intelligent or behave intelligently. If you don't believe me, go to some frat parties and you know exactly what I mean. So intelligence and humans are not necessarily the same class of entities or behaviors. So that's another possible source of confusion about these kind of scenarios. But this test is very practical. You can actually implement this. And you can execute it, and you can test it, and you can collect data on this. And this is not just some abstraction. It's, you know, you can actually do this, and people have done this lots of times. And there's lots of variants on these kind of tests. There's reverse Turing tests and other kind of variations on it. There was mechanical Turk called just the Turk in the 1700s that played chess at a grandmaster level. And for about a century, it fooled most of Europe that it was a mechanical computer that can play chess, to a very sophisticated level. It turns out it had a little guy in the box. And that little person actually was a chess master. And sometimes when they opened the box to the audience to show them there's mechanisms inside, gears and pulleys and whatever, the guy would scramble from left to right. They would only open the left door and they would scramble right. They would open the right door, he would scramble left inside the box, so they couldn't see the guy. But it was a little person. So this was like almost like a Turing test for an audience. And most people who saw it believed that this is a very clever, intelligent machine, that can beat humans in chess. And he operated the mechanical hands of this mannequin on top that actually moved the pieces on this board that was sitting on top of the box. Very clever hoax, but hoax nevertheless. Well, fast forward about 3 centuries and 2.5 centuries. In the 1900s, there was a program called ELIZA. It was the first so-called chatterbot that convinced people it was a psychoanalyst, a therapist, a psychologist that would interact with you using text over a teletype. And so if you typed in a question like saying, I hate my father, it would type back, why do you dislike your parents? And it would sound like it's empathizing with you. And a lot of people felt much better after they interacted with it for half an hour, saved themselves fees for a real psychologist. So that fooled a lot of people, actually. And the HAL 9000 computer from 2001 Space Odyssey, Arthur C. Clarke said that he modeled the HAL 9000 after this program, ELIZA. It was named after Eliza Doolittle from George Bernard Shaw's Pygmalion. Stage play My Fair Lady was based on that. So chatterbots now appear regularly in chat rooms and on dating sites, websites. So, before you fall in love with some entity on the other side of the computer, on a chat room or a dating website, be careful because it could be a bot talking to you, and you could be catfished. These terms didn't even exist 10 years ago, but it could be very embarrassing, and not to mention, emotionally humiliating. So just be cautious out there. But these chatterbots are really, really good now. A lot of people are fooled by them, and that's the whole point. They're almost passing the Turing test. So whenever somebody gets catfished, by some fictitious entity on the other side, they almost fail the Turing test in some sense, or at least they misjudge the other entity in a Turing test kind of a thing, especially if it's a bot. So there's yearly conferences now and competitions about chatterbots, and they're getting very, very sophisticated. Just so you see how sophisticated they get, here's an actual dialogue from a chatterbox competition. This was 10 years ago. It wasn't even recent. It fooled roughly a quarter of the judges. Turing said if you can fool 30% or more of the people consistently, you're past the Turing test. Because you're not going to go for 100% because most of us couldn't fool a panel of judges 100% of the time. What if they asked you to write a limerick? Most of us couldn't come up with a clever limerick in 2 minutes or whatever. What if they ask you for a winning chess move in 2 moves, showing you a board position? A lot of us will not be able to consistently convince a panel of informed judges. So 30% is enough, Turing said. Anyway, it says, what's your favorite novel? And the bot says, I often read telephone books or some poetry. Judge says, typical computer. And the bot says, you tend towards generalizations, but I must admit, so do I. However, my generalizations are firmly grounded in statistical theory. So it's a bit snarky, kind of a reply. The judge says, what do you think of somebody's enthusiasm for having machines take over the world? And the bot says, fix up the world a bit first, then I'll take it over. So that kind of snarkiness and irony and witticism, you don't expect that from a bot or a software engine, and that's exactly the way they behave. This is a real interaction from a real test, actually, the competition. This was 10 years ago. Now it's even better. So you see, it's hard to tell if it's not a human on the other side. They're getting arbitrarily more sophisticated. So there's lots and lots of international symposiums like that, and Turing test kind of forums and competitions and prizes, and there's even ones that have robots going around some landscape, physical robots, not just chatterbots that produce text, but actual machines, bipeds even that play soccer. There's RoboCop, right? Soccer with robotics. They have to be bipeds and they have to kick a ball. And, I mean, they're no, Beckham, but or Pelé, I don't know, whoever is the greatest soccer players these days. But still, they get better and better. It's actually hard to do biped motion, even if you just want to walk or jog, never mind play soccer or anything competitive. Turns out it's a very difficult problem to control. But so now we can change this test or these questions that we saw earlier. Instead of saying which ones can think, we'll say which ones of these can pass the Turing test. Now, this is testable. This is not some philosophical question. We can set up a Turing test and run these things through Turing tests and then see what happens. So, obviously, some of them are strictly software, like HAL 9000 and the Matrix Agent Smith and whatever. Some are equivalent to one another. We already saw in computational universality lecture that abacus and Turing machines and supercomputers and iPhones and even biological computers or AND and OR and NOT gates, these are all equivalent systems. So whatever the answer is to one of them is the answer to all of them. How many get that? They're in the equivalence class. And of course, all humans are in the same equivalent class. It's not about IQ, it's just about general intelligence. So we're all the same here on the high end, and the question is which one of these can pass the Turing test? Most people will realize not rocks can't do it, viruses and bacteria and insects can't do it. They can't even speak language, natural language, much less pass a Turing test. Dolphins and chimps, well, they're very smart, and some chimps, we already said, can sign language, and but they can't pass a Turing test. They have a hard time typing or constructing grammatically correct sentences in any natural language. They think very primitively. They can't abstract anything, and as far as we know, very much. They can do some levels of abstraction. They did tests where they painted a dot over a dolphin's back in a way that the dolphin can't see because they have a rigid body. But there was a big red dot now on the back of the dolphin. They put a mirror underwater. And the dolphin would swim around the mirror and look at itself. And it's hard to tell if it's self-aware or not, but when the dolphin saw the dot, it started to do this. It knew it's a dot on him in the reflection. So there was self-awareness there, actually, of some kind. There's all sorts of tests like that. It's really quite amazing, actually. Think about the level of abstraction that must go in the entity's brain in order to realize that dot, it's really on him, because it's very indirect. It's just a reflection. A reflection may not even look like it or one of itself kind to it and that kind of thing. It's not just visual. It's higher level than that. Anyway, this region we don't know if it can behave intelligently, but we already saw bots that can behave very much intelligently to fool a lot of people. HAL 9000 on the Discovery ship in 2001 Space Odyssey was highly intelligent. In fact, not just intelligent, but it outsmarted the astronauts on board. In fact, it killed a lot of them. Spoiler. R2-D2, C3PO, highly intelligent. They can pass the Turing test as well. Right? In fact, R2-D2 speaks in beeps, but it's got C3PO to translate. So still, it can communicate with humans via a translator. Data on Star Trek can definitely pass the Turing test. In fact, there was a Star Trek episode where Data claims to be sentient and demands to be promoted in Starfleet and possibly get his own ship command one day. And of course, they all kind of looked at him with alarm, and he was a useful bot to have around, but when they weren't quite ready to have them be sentient like they are with all the rights and responsibilities thereof. So it's an episode about bias, about prejudice, actually, disguised as robot asking for equal rights. Women had to go through that 100 years ago in this very country. Minorities are still struggling with it in this very country, this very day. But at the end, he basically convinces Starfleet Command that he is sentient, and he acquires all the rights and responsibilities as other people. How many have seen this episode? It's this beautiful episode. It's about the Turing test, although they don't call it that, or they probably mentioned Turing somewhere in there. Terminators in the movies were able to not just pass the Turing test, they were able to convince people that they're human. In fact, they were hard to distinguish from non-humans. Agent Smith in the software, in a Matrix, he's a piece of software, but still the same thing. Cylons in Battlestar Galactica, they can also pass the Turing test. In fact, they can do more than that. They fooled humans into thinking they're physically other humans, not just be able to type text and interact like other humans, but look and feel and behave like other humans. In fact, some of these Cylons in the show didn't even know they weren't human. They themselves thought they were human, so they even fooled themselves into thinking that they're other humans. So that's how human-like their behaviors were. And of course, humans are humans, and they can pass the Turing test. In fact, we constructed the Turing test, so yeah, we can pass it if we constructed it. It's all basically reference relative to us. So now you can answer the question much more decisively. Now, the only questionable region is here in the middle. Can these machines that we have now today, our iPhones and supercomputer and cloud machines, can think? Not necessarily right now, but in 5 or 10 or 20 or 50 years or 100 years. And most people now beginning to believe that is true. And there's smarter and smarter bots these days, and cars already self-drive themselves on the freeway, and it's quite sophisticated. Yeah?
If HAL 9000 is supposed to be completely software, why doesn't it fall under the same class as Turing machines?
Well, all of these are like Turing machines. They can simulate Turing, and Turing machines can possibly simulate all of these. But remember, in the movie, we aren't getting specifics into the movie, it didn't have a lot of actuators and moving arms or biped kind of apparati that kind of moved around like Terminators and things. He was basically in control of the ship, but it was very passive, right, in terms of physical movement. It had no large appendages or arms or couldn't lift things. It was basically a piece of software implemented on a piece of hardware, but it was basically a box, as opposed to Terminators, which actually roam around and chase you down the hall. That's a bit different. That's very active. That's not passive. That's all I'm saying there. So the question of intelligence and sentience, we've been pondering that for a long, long time. Very interesting. There's a famous cartoon that says, on the internet, nobody knows you're a dog. How many have seen that? So that's essentially a reference to the Turing test in an oblique way. In the movie Blade Runner, Decker is trying to figure out if this thing is a human or an android. It turns out that she's synthetic. She's an artifact, but behaves very much like human. In fact, she doesn't even know that she's not human. They made a sequel to that. I think the original was still better. How many saw the original, Blade Runner? Beautiful movie. Again, about essentially the Turing test as a main premise there. They call it the Voight-Kampff empathy test in the movie, but they really meant the Turing test. I'm not sure why. Maybe they had some copyright issue with Alan Turing's estate or something for using that phrase or term, or maybe, who knows? But they should have really called it a Turing test. Any questions about any of that so far? It's just a very, very intriguing set of concepts. So the Turing test is not without criticisms. First of all, it's behavioral only. It's only how the thing behaves, not whether there's something really there that we call sentience or intelligence or self-awareness or humanness. It's just the I/O behavior of that thing. So it's comparative to humans. It's not some absolute test for intelligence or sentience. It's just how similar to human behavior it is. We already said some human behavior is not intelligent and some intelligent behavior is not human. So the two are not the same thing necessarily. And some people anthropomorphize objects. A lot of people will tell you that their pet dog or cat or pet ferret or whatever just loves them and misses them when they're gone, and has a lot of empathy for them and really cares about them and knows what they're telling it. And so humans tend to anthropomorphize things, and for better or worse, we tend to do that. So that's potential pitfall in such a test. And a lot of people are easy to fool, right? There's this bank deposit scam on the web, where they say, we'll send you $50 million and we'll give you 10 million of the 50 if you just give us your account number. And that, how many have seen or heard about such things? People fall for that. So a lot of people are very gullible. How do we know that some people still fall for that scam, these phishing scams on the web, even though they sound ridiculous? How do we know that? Because they still exist. If nobody fell for them, they would have stopped doing that 10 or 15 years ago. It's just Darwinian evolution on the web. So yeah, people are easy to fool, and the Turing test is about fooling or convincing somebody on the other side that something is true or not true. And there's debate, among philosophers and psychologists whether intelligence is real or simulated, and whether one makes a difference. There's a scenario called a Chinese room. That's another criticism of the Turing test. The Chinese room basically says there's a computer here that behaves intelligently, running a piece of software, but it's happening in Chinese. And it's passing the Turing test in Chinese. So then what you do is you take away the computer and replace it with a person, and the person doesn't know Chinese, but it's still simulating the software there on paper, with a pencil on paper, and it's still interacting with the same tester on the outside exactly the way it did before, because it's the same software running now by hand, tedious line by tedious line, but a person is running it, and he doesn't speak Chinese. So the question is, what in this room still is intelligent or is passing the Turing test? It's no longer the person. The person doesn't even know Chinese. He doesn't understand what the inputs and outputs to this box is, this Chinese room box. Is it the software? Well, the software is just one long string. We already saw strings and programs are equivalent, right? So is the string an intelligent string? It's hard to wrap your mind around exactly what's going on here and where the intelligence is embodied or imbued in whether it's in the string, because it's certainly not in the person now that doesn't even understand what is being asked or answered. He's just happening to be accomplishing that according to a rigid set of instructions. That's just a program. So that's one of the objections to the Turing test or criticisms, and raises a lot of interesting questions in behavioral psychology. And there's something called a reverse Turing test, when instead of a computer trying to convince a person that it's another sentient, intelligent entity, here the person is trying to convince the computer that the person is not another computer. So that's called a reverse Turing test. The convincing is going in the other direction. And one example of that is CAPTCHAs. How many can see that's a reverse Turing test? You need to prove to the computer that you're not another bot. And you can do it with reading weird fonts, and there's a kind of a arms race about CAPTCHAs and anti-CAPTCHAs and so on. The earliest robotics kind of story or scenario was Mary Shelley's Frankenstein, 1818, 200 years ago. And it raised a lot of questions about sentience and so-called the Frankenstein complex, what we call now the Frankenstein complex, the excesses of technology, the notion of mad scientists, runaway consequences, unintended consequences of technology and science. And there's other incarnations of these Frankenstein stories. So Terminator is a Frankenstein story, right? How many could see that? So you create something, you didn't anticipate all the consequences, it turns on you, and it makes you very sorry you ever created it, and so on. HAL 9000 is a Frankenstein story, under the same isomorphism, right? The computer being the Frankenstein monster. And then there's a lot of movies about sentience and robotics, right? Lost in Space and Forbidden Planet and The Day the Earth Stood Still. Even early movie making, Metropolis here was black and white movie, silent film, beautiful film. Silent Running with three little robots called Louie, Dewey, and Huey, and they're their inspiration for R2-D2, actually. How many knew that? Bruce Stern, right? Great science fiction film. It predates Star Wars, of course. And of course, Terminators of all kinds. Westworld, the old rendition. The new one is much better. It's very. How many have seen Westworld, the new show? Amazing show. It's again revolves around the Turing test and issues about sentience and agency and intelligence, and whether machines have rights and responsibilities like we do, and whether we can just use them for whatever purposes we might want. Beautifully done. And of course, no discussion will be complete without the Borg in Star Trek. Will Smith is after Asimov. Asimov wrote The Laws of Robotics, these robotic stories famously in the 1930s and 40s. And then there's some humorous movies. And Bicentennial Man, also very good. Robin Williams starred as the robot, the sentient robot there. Very nicely done. It's a very sophisticated movie. And of course, the robot stories by Isaac Asimov, who coined the 3 laws of robotics. How many read some of his novels, Isaac Asimov? He did this in the 1940s. In fact, he coined the word robotics. The word didn't exist before he came around. And he did this before computers existed. This is the 1940s. The first electronic computers were just built in the late 40s and early 50s. And he was already writing entire novels about the consequences of this kind of technology and artificial intelligence and synthetic sentience and interactions of robots with humans and so on. And he famously came up with the laws of robotics. These are some actual applications. These are products. These are devices that are real. This is not science fiction now. And they're in the ground, they're in the air. The military uses them. They go around killing people, predators, predator drones, Reaper drones. So robotics are now all over the place, right? They're in the air, they're at sea. Here are some micro robotics, like little tiny drones, and they're at sea. And my favorite self-driving cars, which I call Turing machines with an O. My favorite Turing machine these days is a Tesla Model 3, and we mentioned in the email we'll have a demo in mine, which kind of looks like this. And you're welcome to come Sunday at 1 in the afternoon. We'll take some joy rides around the block. I get to drive, by the way, insurance thing. So we'll see you then, and we'll keep talking about this, and we'll have a Ask Me Anything session next Tuesday, which will be the last lecture. All right, see you then.